In a previous video, we looked at a full solution to an example where you had a saddle point. I think in that example, the matrix A was equal to 8, -11, 6, -9. And from that problem came out two eigenvalues, one of them being -3 and the other one being +2. So there was an example of a matrix that had two real eigenvalues, but one was positive and the other one was negative. Okay. Turns out that for linear systems, differential equations of the form dy dt is equal to ay, that when the matrix A has real eigenvalues, there will be two of them if the matrix is a 2 by 2 matrix, so a 2 by system of two differential equations. If A has real eigenvalues, that the eigenvalues can break down into two categories, where the eigenvalues are real, but there are two, one positive and one negative. The eigenvalues can come out to be positive, positive, or the eigenvalues can come out to be negative, negative. So this is what the textbook is trying to point out at this point, that there are three kinds of equilibrium points. The equilibrium point here is 0, 0, always y is equal to 0, 0, because a times 0, 0 is equal to 0, 0. So 0, 0 is the solution. It's an equilibrium solution. And they're discussing what kind of equilibrium point it can be, and that equilibrium point breaks down onto which of the categories your eigenvalues fall in. So when one of the eigenvalues was positive and negative, this was our saddle point case, and you have a sink when the eigenvalues are both negative and negative, and a source when the eigenvalues are positive and positive, and a saddle is when they're positive and negative. Okay, so let's just go through just sketching a couple of pictures of what is going to occur, or what things can look like in the phase plane. So based on these two conditions, or these three conditions, you always have 0, 0 as an equilibrium point in the three different cases. Right? So I'm drawing three different phase planes here. This is xy, xy, and xy. In the case where the eigenvalues are positive and positive, you're going to have two straight line solutions, one for each eigenvalue. Let's just assume for simplicity that they are these two axes. If both eigenvalues are positive, then solutions will, along those straight lines, tend away from the 0, 0 equilibrium point. Okay, and therefore solutions for what this equilibrium point is called a source. That means that any initial condition you pick, right, and say in these four quadrants, solutions are always going to go away from this equilibrium point here. That's a source for the plus plus eigenvalues. There's the minus minus case, right? And assume for simplicity that the eigenvectors, the straight line solutions, were the axes. The eigenvalues negative means that solutions will tend to 0 along these straight line solutions, and therefore for any other initial condition, the linearity principle says that you have a superposition of solutions, and what that looks like in a picture is adding the two solutions together along the straight lines. You'll have solutions that are tending in to the equilibrium, and this is the case that's called a sink. Okay. And we've seen the saddle example that one of the eigenvalues is positive and the other eigenvalue was negative, and therefore initial conditions that you choose, assuming that the simplest case, that the axes are the straight line solutions, then solutions will tend for a saddle point to have this kind of looking behavior in the phase plane. So this is what's called a saddle. Okay? So anytime your eigenvalues of your matrix break down in these categories, you're expecting phase plane pictures to kind of look like one of the three cases above. Okay? So if we look at a quick example here, okay, let's say that the matrix is -1, 0, 0, -4 up here. Okay? You can see here that, and we've got an initial condition -1, 1. You can see here that your eigenvalues break down into become two negative values, and in this special case the straight line solutions are along the axes. So in the y direction you've got a -4 eigenvalue, and in the x direction you've got a -1 eigenvalue. So here are your two straight line solutions, right? You can use the linearity principle to find your constants k1 and k2, and therefore your solution to the initial value problem is eat this here. Okay. Now let's go ahead and take a look at this case and just kind of track it through and see what's going to happen. You know the two eigenvalues came out to be negative, so you know that in the phase plane what you're going to be expecting to see is the equilibrium here. You're going to expect to see all your arrows flowing into the origin there, because we have two negative eigenvalues, so the solutions are going to tend to look like that's the sink solution. All the solutions go in towards, no matter where the initial conditions are, go in towards the equilibrium 0, 0. Okay? Let's just do a couple. Okay, so what you're seeing here is that both x and y are tending to 0. So if you can see, look at the time plots for your solutions x. X is the black line. X, as time gets bigger and bigger, is approaching 0. And the y, which is the dotted line, as time gets bigger and bigger, also tends to 0. So these kind of plots in the time plane lead to these phase plane solutions that as x and y both get closer to 0, no matter the initial conditions, your solutions always tend in large time to approach the point 0, 0 in the phase plane. Okay? So that's the picture of what we expect to see. The analytic, right, was up for us to kind of go through some of the details of. So let me do that real quick. Skip some steps here. So a good example of a sink, an example there was the matrix A was -1, 0, 0, -4. Okay? The eigenvalues for that matrix, remember you need to find the eigenvalues, figure out what they are by solving the determinant of A minus lambda I, setting that equal to 0, solving this thing. This is called the characteristic equation. And the characteristic equation, right, you've got the code here, the characteristic equation comes out to be lambda squared plus 5 lambda plus 4, set that equal to 0, and when you solve for lambda, lambda comes out to be -4 and lambda comes out to be -1. So there are your eigenvalues. Okay. Now you turn around and solve AV equal lambda V, put lambda equal to one of the eigenvalues and solve for V, and your solution when you solve that system of equations, give me 1 second. Yeah, we decided that the eigenvalues for -4, the eigenvector came out to be the y-axis, and for the eigenvalue -1, and you solve for v, the eigenvector came out to be 1, 0, the x-axis. Okay, so now you have two straight line solutions, y1 of t. We know that it's going to be 0 e to the -4t, and we know that y2 of t is going to come out to be e to the negative t 0. Okay, so you can see that along these straight lines, right, picking an initial condition, notice that y1 of 0 is 0, 1. Right? So if you pick the initial condition here in the xy phase plane, and then look as t goes to infinity, y1 of t goes to 0, 0. This e to the negative 4t gets closer and closer to 0. So initial condition up here, the solution is tending towards the equilibrium. If you chose another initial condition down here, solve, the solution would go in towards the equilibrium point because the eigenvalue came out to be negative. Okay. The other solution, y2, the initial condition was, if you look at y2 of 0, the initial condition is 1, 0, and look what happens as t goes to infinity. As t goes to infinity, y2 of t goes to 0, 0, which means that we're coming in towards 0 along this direction. Initial conditions on this side will do the same thing. Okay. And therefore, okay, we can see our source equilibrium point setting up here. If you continue on to find the initial condition, okay, so now you have y1 of t 0 e to the negative 4t, and you have y2 of t is e to the negative t 0. Then when you find y of t, the solution to your initial value problem, okay, we're looking for k2 times e to the negative t, and k1 would be k1 e to the negative 4t. This is your general solution for any initial condition, whatever it's going to be. We don't know yet. Okay? So now if you specify the initial condition, y of 0, we wanted that to equal to the initial condition 1, negative 1 that was stated in the problem. Then you know that you're going to get k2, k1, putting in 0 here, and that's supposed to be 1, negative 1, which tells you that k2 is 1 and k1 is negative 1. So your solution that goes through the initial condition in question is e to the negative t, negative e to the negative 4t. Okay. So there's your solution that goes through the initial condition 1, negative 1, let's say. Okay. And notice that as t goes to infinity, y of t gets closer and closer to 0. So we're coming in along this way. Okay. So you can see that in the negative eigenvalues case, we're getting this behavior that we're expecting to be what we're calling a source. I'm sorry, a sink. Okay. Whoops, sorry. Trying to bring this over so you can see the plot there. So in the phase plane, yeah, our solutions are looking like a sink. Okay. If you switch this up and look at the source, okay, here's an example of the matrix 2, 2, 1, 3. Okay. Recompute this problem. Sorry, highlighting this. Okay. And we can see here that the eigenvalues come out to be 4 and 1. Okay. You can do that by finding the characteristic equation 2, 2, 1, 3. Okay. Look at a minus lambda times the identity. Look at the determinant of a minus lambda I times the identity. you can solve, and then you can find eigenvalues and eigenvectors. Okay. So the characteristic equation comes out to be lambda squared minus 5 lambda. Solve that equal to 0 for the two eigenvalues in question. Okay. So we have two positive eigenvalues. We should have a source at this point. Okay, and we can see here that all the arrows are emanating out from the origin 0, 0. You can see your straight line solutions. Okay, the straight line solutions, like this problem's kind of tilted on its side a little bit. The eigenvectors are 1, 1, and the other eigenvector is negative 2, 1. So if you're looking in the phase plane, you can see your two straight line solutions. On this side, 1, 1, and negative 2, 1. They're your straight lines. And any initial condition you pick is emanating, going away from those equilibrium. Okay? So specifically for the initial condition, negative 1, 1 here, right? You can see our solution, negative 1, 1, is going to, this orange one here will go away, and both x and y will go to positive infinity. That will make sense when you solve the analytic equation. Go through and solve for all the initial conditions. K1 will be 1/3, K2 will be 2/3 to meet the initial condition negative 1, 1. Here is your solution that you're going for. You can work through the details here. Okay, the details of these steps. You should do that now after you pause the video. There's the solutions you're working towards, and here's the x and y solutions. Notice that they both have positive exponentials, so as t goes to infinity, x, the first entry of this matrix, is going to go to positive infinity, and y, the second entry, is going to go to positive infinity. So time plots here will say that both of your time and both x and y and positive time shoot off to infinity, and that corresponds in the phase plane to the source behavior. Okay, so I think we've looked at the source, sink, and saddle, and I think we've gone through all the details there. The rest is just to practice the problems.